Alright, now we're going to look at another preemptive scheduling algorithm which is called round robin. This is one of the most popular scheduling algorithms. So what happens here is we fix something called a time quantum or a time slice, and then every process is executed for as many units as the time slice. So if your time slice is defined to be 2 cycles, then you execute every process for 2 cycles, then you go to the next one is for 2 cycles, the next one is for 2 cycles, and so on and so forth. Then you come back to the first process again for 2 cycles. So basically it is first come first served with a time slice. So we'll look at a couple of examples. The first one is the one given under round robin in your textbook. 3 processes we have. Again, we assume everything arrived at the same time in this sequence. P1 needs 24 units, P2 needs 3 units, P3 also needs 3 units. We assume a time quantum of 4 milliseconds or 4 cycles. So for the first 4 cycles, we use P1. Then for the next 4 cycles, we should use P2, but P2 needs only 3 cycles. So we'll give it 3 cycles and we wrap up. Then for the next 4 cycles, we should be using P3, but again P3 needs only 3 cycles, so you give it 3 cycles, P3 done. Then next 4 cycles P1, and then if you see there are no other processes except P1, so until P1's burst time becomes 0, you keep giving P1, P1, P1. So this is not a very representative example in my opinion. So let us go back to what we saw here for shortest remaining time first, and we'll try to solve this one using round robin. Yeah, so this was the example given. We have 4 processes P1, P2, P3, P4, and for the purpose of this example I am going to assume all of them arrived at the same time, 0. I don't want to complicate things by including an arrival time, and the time quantum or time slice we will be dealing with is 2 units. So let us try. So the logic is very simple. You start in the order in which the processes are. You allocate 2 units for every process, and then the burst time reduces accordingly. So at time instance 0, I will do P1. At time instance 1, again I will do P1. That is 2 units for P1. So this 8 becomes a 6. Now for the next 2 units it will be P2. So is this visible? Yeah, P2, P2 at 3 and 4 respectively, and this becomes a 2. Now for the next 2 units is going to be P3, P3, 5 and 6. The 9 becomes a 7. Next 2 units P4, P4, 7, 8. So this 5 becomes 5 minus 2 is a 3. Again we go back to P1, 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 9, 10. This 6 becomes a 4. 2 units for P2, 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 11, 12. This 2 becomes a 0. So we are done with P2. We finished with a 12 here. So let's continue. P3, P3, 2 units. This 7 becomes a 5. 2 units for P4, 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 15, 16. So this 3 becomes 3 minus 2 is a 1. Again you come back to P1, 2 units. P1, P1, 17, 18. 4 becomes a 2. P2 was over already. P3, 2 units. P3, P3, 19, 20. This 5 becomes a 3. P4 needs only 1 unit, so you give it that 1 unit and you finish off with P4 again. Go back to P1, give it 2 units. P1, P1, 22, 23. So we gave P1 2 units, so that's it with P1 also, we are done. So P3 now needs 2 units. P3, P3, 24, 25. Now this 3 becomes a 1, and all other processes are done. This is the only thing pending. So again you go for P3, 26, and with that we reach the end. So this is what our Gantt chart looks like. So now this is how you do the Gantt chart for a round robin scheduling. And one more thing I would like to draw your attention to is how exactly we compute the wait time. So because this is a preemptive scheduling algorithm, the wait time is not just the time between entering the queue and entering the Gantt chart, right? So for example, I'll teach you to compute the wait time for one process, and I hope you will be able to extend the same for the rest. So you take P1, it entered the ready queue at time 0 and it entered the Gantt chart also at time 0. So over there is a 0 unit wait time. Then it leaves at 2 and then it comes back at 8. So 8 minus 2. For these 6 units it was still in the queue, right? So that is wait time. Again it leaves at 10, comes back at 16 plus 16 minus 10, another 6 units that will be. It leaves at 18, comes back at 21. So 21 minus 18, and then it leaves at 23 and it doesn't come back. So it is over. So which will be, this is a 6, this is a 6, 21 minus 18 is hopefully 3. So 12 plus 3, 15 units is the waiting time for P1. So I'll do one more example, P2. So this was P1. We'll do P2. I apologize for my horrible handwriting. So P2, it entered your chart at 0. It entered your queue at 0 and entered the chart only at a 2. So it waited there for 2 units. And then it leaves at 4 and comes back at 10. So 10 minus 4, which is a 6. Then P2 leaves at 12 and it doesn't come back, I guess. So it is an 8 unit wait time, and so on and so forth. So this is how you compute the wait time. The turnaround time is very simple. The time it entered the queue is 0 and whatever time it finally exits the Gantt chart, the last time. So if you look at P1, it leaves at 23. It enters at 0 and leaves at 23. So 23 units is the turnaround time. If you look at P3, it entered the queue at 0 and leaves the Gantt chart at 26. So 26 units is the turnaround time, and so on and so forth. So that is round robin scheduling. Okay, so we saw the round robin scheduling and hopefully it makes sense to you, the example, and especially what I would like to draw your attention to is this is how we compute wait time for a preemptive scheduling algorithm. For non-preemptive, it is very simple. Arrival time to the time it gets picked up and put into the Gantt chart. But for preemptive algorithms, it is that plus all the intermediate wait time. So from the moment it is removed from the Gantt chart, intermediate at some intermediate stage, to the moment it is put back again for the next iteration, those waiting periods also need to be considered. So that is a point I would like to draw your attention to. That's that. So if you look at this, the thing is, the performance of the round robin algorithm depends heavily on the size of the time slice. So if your time slice is very large, the smaller processes are going to get completed in one iteration itself. So in one sense, it becomes almost like first come first served. Whereas if the time slice is very small, then there is going to be a large number of context switches. Context switch, I hope you know by now what it is. When one process leaves and another process comes, that data transfer needs to take place. So after every one cycle, if you're going to do context switch time is overhead, right? In that time, nothing is getting executed. So that is a waste of time. So if your time slice is very small or if it is very large, in both cases, we are wasting time. So we need to have a time quantum or a time slice which is somewhere in the middle, not too much, not too little. And that you can see that the turnaround time also depends on the time quantum. So yeah, that's it about round robin. In many ways it is definitely better than your first come first served and all, because no single process has to wait an indefinite amount of time, which is what happened in FCFS. So everyone gets a bit of chance, but the problem here mainly is context switch. After every k cycles you have to keep switching. That's a lot of overhead. And the other problem is the time slice itself is something you have to fix. It is not, there's no hard and fast rule. So if your choice is not optimal, then it could cost you a lot. So that's it about round robin.